Okay, so we know that we can write any exponential of one base with, it could be written in terms of an exponential of another base. Say you wanted to write 3 to the 4th with a base of e instead of a base of 3. All you have to do is think of the question, 3 to the 4th power is the same as e to the what? And then just figure out what that thing is. And what that thing is going to be if you take the natural log on both sides. And of course, when you do that, you'll be able to use the power rule on the right side, and you'll have x times the natural log of e over there. And the natural log of e, remember, is just 1. So x times 1 is x. And so x would be the natural log of 3 to the 4th power. Another way to write that would be e to the 4 times the natural log of 3. So if you want to write 3 to the 4th power as e to some power, that's what it is. It's e raised to the 4 times the natural log of 3. So e to the exponent times the natural log of the base. The rule, the way that your book has this written, is let t and b be real numbers, where b is greater than 0 and b is not 1. Then b to the t power is equivalent to e raised to the natural log of b times t. The population P of T of a culture of bacteria is given by P of T equals 5,000 times 2 to the T over 4, where T is the time in hours after the culture is started. Write the rule for this function using base E. So P of T equals 5,000 times E raised to the natural log of 2 times T over 4. So that's exactly what that statement up there says, which we figured out on the last slide. That is 5,000 e raised to the natural log of 2 over 4 times t. And if you punch that into your calculator, you get about 5,000 e to the 0.17329 t. So that is how you could write this function with a base of e instead of a base of 2. So find the population after 12 hours using both forms of the function of part A. So if you use the base 2 function, it's going to look like that because you're putting in 12 hours for your time. And so if you multiply that out, you're going to get 40,000. If you do it with the E base, of course, you're going to get the same answer. Okay, so we've talked about exponential growth, like population growth. Now we're going to talk about exponential decay. Right? This is when something shrinks over time instead of growing over time. It shrinks at an exponential rate. And this function, q of t equals q sub 0 e to the negative kt, looks exactly like the growth function, except now there's a negative sign on kt, because now it's 1 over e to the positive kt, which means you have this fraction that its denominator, as time goes by, it's getting bigger and bigger. That denominator is getting bigger and bigger, which means that number is getting smaller and smaller and smaller. Now we're talking about shrinking, something shrinking. One of those things is carbon-14. Scientists have determined that the half-life of carbon-14 is 5,730 years. Q of t equals q sub 0 e to the negative kt. Q of t is the amount of carbon-14 remaining after t years. So if we use that half-life as our t, so Q of 5,730 equals Q sub 0 e to the negative k times 5,730. So we know Q of 5,730, we know what that is. It's half the initial amount. So we can put that right here, Q sub 0 over 2. And then the right side of the equation still looks like this, e to the negative kt. So now I can cancel the Q sub 0, and I'll have 1/2 is equal to e to the negative 5,730k. And now I take the natural log on both sides, and I will have natural log of 1/2 is equal to the natural log of e to the negative 5730k. So now I can use the power rule to get k by itself. So natural log of 1/2 is equal to negative 5,730k natural log of e. And I know that the natural log of e is equal to 1 1 times negative 5,730k is negative 5,730k. So I can cross that natural log out and then divide by negative 5,730 to find k. And k is going to be about negative 0.000121. So that's my k for this function, and so I can write the function q of t is equal to q sub 0 e to the negative 0.000121 t. So an archaeologist uncovers human remains at an ancient Roman burial site and finds that 76.6% of the carbon-14 still remains in the bone. How old is the bone? Round to the nearest 100 years. We found out there is 76.6% of the carbon-14, and what that means is 76.6% of the original amount is left. So that's going to go on the left side of the equation. 0.766 of the original amount is left. On the right side of the equation, we've got q of 0, e to the negative 0.000121 t. We're looking for t because we're trying to find out, okay, this is how much is left. How much time has it been since the beginning? So I know how old this thing is. All right, so the q sub zeros go away, and we can take the natural log on both sides, and that is going to be natural log of e to the negative 0.000121 t, and then we will use the power rule to bring that down in front. And we know that the natural log of e is 1, and if you multiply something by 1, it doesn't change it. We're going to divide both sides by negative 0.000121. So natural log of 0.766 over negative 0.000121 is going to be the time. We get about 2,200 years. And so that's how that works. So a exponential decay function is going to be a function where the exponent on e is negative. All right, logistic growth models. All right, we're back to growth models. Remember before when we talked about the population of California and how it would take 88.86 years for that to double. So we said it would double by 2098. So that basic exponential growth function gave us that prediction. That basic exponential growth function, it assumes that populations can just grow and grow and grow and there's nothing to stop them. But that's not actually true, because population growth is limited by things like how much land there is, or how much food there is, or all these things. Populations can't just grow, without anything pushing back. So the logistic growth model is a model that kind of flattens out that curve. It kind of doesn't let it just be this exponential thing that just keeps going up and up and up like crazy. So you can see the graph here. It starts out looking like an exponential function where it's shooting up pretty quick, but then there's a point of inflection where it kind of levels off, and then there's a line y equals c that it can never go above. So this function was created to take into account more things about population growth so that it gives a clearer understanding of what's really happening. There's this theoretical limit to how big a population can actually grow. We're not talking about where this function came from or how it was figured out. So we're just going to look at how this works and what the difference is between this and what the other function told us about the population. So the population of California, P of t in millions, can be approximated by the logistic growth function P of t equals 93.3 over 1 plus 1.5 e to the negative 0.013 t, where t is the number of years since the year 2010. All right, so this is the model we're going to use this time. And we're still looking at t being the number of years since the year 2010. Part A says determine the population in the year 2010. Well, that's when t is 0. So P of 0 is going to equal 93.3 over 1 plus 1.5 e to the negative 0.013 t, but t is 0, so we're going to just put a 0 there. And so it's just going to be 93.3 over 2.5. It's about 37.3 that you can see right there. We had 37.3 as the initial population. So it's the same problem, but we're using a different model. So use this function to determine the time required for the population of California to double from its value of 37.3 million in 2010. And then we're just going to compare the result to example 3. So for it to double, it would need to become 2 times 37.3. And for this function, we have 93.3 in the numerator, and in the denominator, we have 1 plus 1.5 e to the negative 0.013 t. And so now we just need to solve for t. So if we multiply both sides by that denominator, we're going to have 1 plus 1.5 e to the negative 0.013 t times 2 times 37.3 equals 93.3. And then we can divide both sides by that, and we'll be left with 1 plus 1.5 e to the negative 0.013 t equals 93.3 over 2 times 37.3. We're going to subtract 1. So we can just get rid of that 1 and move it over here, make it minus 1. And then we are going to divide by 1.5. So we'll have e to the negative 0.013 t is equal to 93.3 over 2 times 37.3 minus 1 all over 1.5. That's lovely. All right, so now we can take the natural log on both sides. We will have the natural log of e to the negative 0.013 t is equal to the natural log of 93.3 over 2 times 37.3 minus 1 all over 1.5. So that's going to be negative 0.013 t times the natural log of e, but that's just 1, so I'm not going to write it, but be careful. And that equals all that stuff. And so I'm going to punch all that into the calculator. I'm going to say 93.3 divided by, in parentheses, 2 times 37.3, close the parentheses, and then say minus 1, and then hit equals divided by 1.5 equals, I'm going to take the natural log, and now I'm going to divide that by negative 0.013. And that's going to give me 137 years. So t is about 137 years. So you can see that now it's going to take longer for that population to double. According to this model, it won't double in 88 years like that other problem. It's going to take 137 years to double. This function takes into account more things that might slow the population. And so that's why this function is different from the original function. It's called a logistic growth model. And that'll be the kind of model that you might be able to create later, and you'll understand it better. Okay, and then it asks, what is the limiting value of the population of California under this model? And the way we can figure out exactly what that is, remember, this is a rational function. T is in the denominator. And so what is this approaching is what we're saying. All right, so we got the 93.3. That's not going to change no matter what T is. The 1 also is just a constant. It's the e to the negative 0.013 t times 1.5 that is going to be approaching something, okay? The bigger t gets, when t gets very large here, 1.5 e to the negative 0.013 t, so another way to write that is 1.5 over e to the positive 0.013 t. And so you can see that this is a fraction, and it is, when t gets really large, that fraction is going to get a denominator that is getting humongous. And as that denominator gets humongous and the numerator doesn't do anything, we see that that's going to approach 0, because as the denominator gets huge, the number approaches 0. It's getting tiny. So that means that this is approaching 0, which means that the limiting value on this is just going to be 93.3 over 1. So that limiting value would be 93.3 million people.